Hello and welcome. In this video, we are going to take a look at triple and polar integrals. So the idea of a triple integral, recall that we have some sort of, for a double integral, we have some sort of surface hovering over the top here, some sort of three-dimensional surface. And we started off with some rectangular region where x went from a to b, y went from c to d. But now we're going to have also, within each one of these French fries, we've described each one of these rectangular prisms here as individual French fries, and we would find the volume of that one French fry and then add the volume of the next French fry over to it, and we would continue doing that until we'd sum up all of these rectangular prisms, their volumes that is. But imagine that instead, we now want z to go from some starting value to some ending value. And so what we'll do is, rather than take the volume of each one of these French fries, we'll find the volume of each one of these individual cubes. And so basically we'll take a French fry, we'll split it up into smaller cubes, find the volume of each one of those individual cubes, and only then will we move on to the next French fry and again subdivide that into individual little tiny rectangular prisms. They don't necessarily have to be cubes. I guess I'm referring to them as smaller cubes because they roughly look like that whenever we think about each one of these as having a height of dz. So now we're going to incorporate a dz into here, and that's going to be the width of, or the height of each one of these individual rectangular prisms. So looking at R, we see that in this picture, R is the region where x goes from a to b, y goes from c to d. If we computed double integrals, we would see each rectangle in R multiplied by height in order to find the volume of a French fry. So again, this is how we did it previously, where we just had individual French fries and found the volume of those and then summed those volumes. The integral to compute the volume in this picture would look something like this. If our area, our region was rectangular, the integral of f of xy, that's the height, multiplied by the width, multiplied by the length. And so we could think about these as being little individual dx's, these as being little individual dy's, and the height of this thing as being f of x comma y. So when we multiply these three things together, we get volume, and now we want to sum across all of the dx's from x goes from a to b and y goes from c to d. And so we sum up all of these products, resulting in volumes of these French fries. But imagine we took each French fry and split it into small rectangular prisms. To find the volume, we now have something like this. So now notice that our triple integral is just our double integral, and but now we're going to have z going from some value of p to some value of q. So it's no different here. The only real difference is now we're going to do this at each individual height. So if you remember, the outer integral is the one that we start at. So that means the way this will visually look is that first we're basically going to add the volume of all of these little tiny prisms in this first dz. So that's our outer integral here is with dz. So we're going to basically add across the entire region R for just our very first dz. So maybe we're going to go, maybe 1, 2, 3, 4, and then the second row 1, 2, 3, 4, and then the back row 1, 2, 3, 4. And only then will we iterate to the next dz, and we'll focus just on that elevation, and now we'll sum all these 1, 2, 3, 4, and then the ones in the middle row and the ones in the back row. The advantage is that we can specify where z begins and where it ends. While not obvious, our volumes from the previous lessons always were between our surface and the xy plane, but they no longer have to be. So we assumed before that our integral, if we had a surface, some sort of three-dimensional surface floating above here, that our volume was always basically all of this below here and being contained by the xy plane. But now we can find volumes between two surfaces if we wanted to. So they're pretty similar in setup. And we're going to use a triple integral calculator now. If you just Google triple integral calculator, there's a good Wolfram Alpha widget that will do this very easily. But here's the link to their triple integral calculator. So find the volume under the surface, f of xy equals xy plus 3 over x greater than 0, greater than or equal to 0, y greater than or equal to 0, and under the quarter circle with radius 2 in the first quadrant, do this with a double integral and with a triple integral to see we get the same answer. Okay, so in this case, with the double integral, we would first of all start off sketching the surface, the region. So let's sketch the region, which is a quarter circle with radius 2 in the first quadrant. So that would look something like this. We'd have this quarter circle here. This is going to have radius 2. So that means it's going to have the form x squared plus y squared equals 2 squared. X squared plus y squared is radius squared. And so we have some sort of surface floating over this xy plane. And so to find the double integral, well, it depends on whether we want to slice into vertical strips or horizontal strips. So let's just go ahead and say we started at x equals 0. We slice this thing into a bunch of vertical strips like this, and then we stopped over here when we reached x equals 2. So that means our outer integral for the double integral would be x from 0 to 2 dx. And now my value of y within each of those strips, remember we have to start at the bottom and then work our way up until we slice up to the top of the circle. And once again, in the next column, we do the same thing, slice to the top of that. So that means we're going to go from 0 to the top of that quarter circle, which is specified by, let's see, if I subtract x squared from both sides and take the square root, I get y equals plus or minus the square root of 4 minus x squared. I only want the positive values of y. I don't want the bottom portion of this circle. So I'm just going to have to the positive square root of 4 minus x squared. And then now we want to, so we have dy times dx. That's going to be the area, recall, of each one of these little rectangles multiplied by the height of that, which is going to give us the volume of that French fry. And the height of that function is xy plus 3. To do this with a triple integral, we would do the same thing, except rather than to have our function inside of here, we would now say let our two outer integrals here be dy and dx. So I'll still make myself a little bit of space here, dy dx, but then in the middle I'll have dz. And what that will give me the volume of is, recall that what we're doing is we're splitting this French fry into multiple individual, I guess you could call them mini French fries if you want, but we're breaking them up into these, and these have dimensions of dx by dy by dz. So we're going to choose to sum along each of the French fries first. So we want to sum this way, and only then will we move to the next French fry. So we want dz to be in the innermost integral. And so our two outer integrals will still be our region much in the same way. So if you set up your region, your two outer integrals could be those that specify what your region is. That is the semicircle or the quarter circle. Now for z, my inner integral is going to specify where z starts and where z begins. So I always want to start from, well, it says under that surface, so that means from z equals 0 all the way up to z equals the function, which is xy plus 3. And since this already takes care of volume right here, this is already volume, I don't actually have an integrand. So you could leave the integral like this, or you could put a 1 in there. Otherwise, if you put a 2 or a 3 or a function in there, then you're now taking your volume and you're multiplying it by something. Well, as long as we let that something be 1, then all we're computing is total volume. So let's go ahead and check out this integral calculator. And so here we have the double integral calculator. You can see that we get a volume of 11.42. There's my function, dy dx. X goes from 0 to 2. Y goes from 0 to the square root of 4 minus x squared. If I do it with the triple integral calculator, lo and behold, we get the exact same answer. F of x, y, z that's our function in here, which we wanted to be 1, since dz, dy, dx calculates volume already. Z goes from 0 to xy plus 3, and x and y, same values as before. So you can see that works out quite nicely. Now, where this would be super convenient is, say we wanted to find the volume between two surfaces, f of xy equals xy plus 3, and g of xy equals xy minus 3. So you can see that the purple surface, that's the one on the bottom, that's g of xy, and f of xy is this kind of teal surface, and we want to find the volume in between these two surfaces. So we couldn't really do that with the double integral. With the triple integral, we can, because guess what? All we have to do is change our boundary here on this integral. For z, rather than starting at 0, we have it start at xy minus 3. So all we have to do here is just change our lower bound to say, well, we don't want it to start at 0. We want this to start at the surface underneath, which is the g of xy, from xy minus 3 to xy plus 3. And then we can, of course, check our work and just change this to xy. I'll just copy and paste this guy here, make our life a little bit easier. So xy minus 3, and when we execute that, we get 18.8496. So another nice example of where this works out well is whenever you're looking at the mass of a three-dimensional object. So suppose that in this case you have a solid shape like a wedge of cheese that has its base, the xy plane, bounded by the x-axis, the line y equals x, and the line x plus y equals 1. Its sides are vertical, and its top is the plane x plus y plus z equals 2. At any point, the density of the solid is 4 times the distance from the xy plane. We're ultimately going to want to find mass. So mass, remember, is a measure that could be in something like grams. And we looked at in a previous lesson at mass for a two-dimensional object or two-dimensional piece of steel that maybe had different densities at different points. But now our density is going to be in a measurement of something like grams per cubic area. So we could look at grams per cubic centimeter. Basically, if you look inside of a three-dimensional object and you want to know, okay, what's its total mass? Well, it depends on its density at every single point, and that density could change along that entire three-dimensional surface. So now when we multiply this by the volume of that little surface, well, guess what? Volume is a triple integral, could be done with a triple integral, and then our function, our integrand, could be the density function. When we multiply those two things together, we get grams as the output. So express the mass of the region in terms of triple integral. So down here I actually have the surface drawn out. So let's go ahead and look at this. So here is what this surface looks like. The problem says that the surface is bounded by the line x plus y equals 1, and by the line y equals x, and by the x-axis. So this is the top view of it. We can see that this corner point over here is this corner point right here, the point 1/2, where those two lines intersect, and we want the volume of, or we want the mass of this surface across that region. So we are told that the density is a function of the distance from the xy plane. So remember, we have lots of densities. We have three-dimensional densities, and so our density function, which I'll just call d of x comma y comma z, right? So your density depends on where within that wedge of cheese you are, and it's 4 times the distance from the xy plane. Well, let's think about a point and think about what this function might look like. If I have, say, the point, I don't know, 1, 0, 3, then what's its density? Well, its density is equal to 4 times its distance from the xy plane. That's this distance here. That's a distance of 3, so we would expect this to have a density of 4 times 3. So what I'm getting at is basically this is just 4 times the z component. It doesn't matter where within this wedge of cheese you are, it just matters how high off of the xy plane you are. So there's our density function. Now, to set up the integral for this, to find the mass, we need to, first of all, find the volume of this surface. So we're going to use the triple integral to find the volume of our surface. And so let's go ahead and take a look at the two-dimensional region here. Here is our region, and so I can break this up a couple of different ways. The way I'm going to choose to break it up is into horizontal strips, because if I break this up into vertical strips, then right when I get to this point here, my function no longer goes from 0 to this line, but to the right of this break, my function goes from 0 to the other line. So to make my life a little bit simpler, and so I don't have to perform two separate integrals, I'm going to break this up into horizontal strips going this way. So I'm going to start at y equals 0. I'm going to continue breaking this up into strips until I reach the top. So that tells me that, I'm going to leave myself some space here, that my y value is going to go from 0 to 1/2. That's where my horizontal strips begin and end. Now my x integral is within each of those strips. I'm going to go from the left line, break this thing up until I hit the right line. Next row, same thing. Start at the line y equals x, make my way over to the line x plus y equals 1. So I'm going to start at the line y equals x, but I need to know what the x value is, so x equals y is the same thing as y equals x. And for this guy here, x equals 1 minus y. So that means this is going to go to x equals 1 minus y. So now we have the region broken up into miniature rectangles, but now we have to take that French fry. So what's staring up at us, what we're looking down upon, is each one of these French fries. So if I again draw this French fry here and say I want to break this up into tiny regions, so I'm going to break it up there and break it up there and break it up there. So my dz is going to go from the xy plane, that's where my cheese starts, and it goes up to the plane x plus y plus z equals 2. The z value for the plane x plus y plus z equals 2 is z equals 2 minus x minus y. So now my inner integral, to sum those individual rectangular prism volumes, I'm going to go from z equals 0 to z equals 2 minus x minus y. And this is now the volume that I've achieved. So dz, dx, dy, that's volume. And we said that to get mass, we need to multiply by the density. Well, the density function is my d of xy, and we said that the density is 4 times the distance from the xy plane. So this is now in density. And if we look at the units, I don't think we were given the units in terms of what mass, what density and volume are measured in, but we have some sort of mass per cubic unit multiplied by dz, dx, dy, which would be cubic units. And so we end up with units of mass. I'm not even going to bother putting this into the integral calculator. You're welcome to do it. This is just a great way to practice setting it up. Now that's really all there is to triple integrals at the most basic level, so we'll go ahead and leave it at that. And we'll look at one more type of coordinate system. Instead of where we focused on rectangular coordinate systems, sometimes we want to accumulate volume along circular regions. So in our very first problem, we had a quarter circle, and our boundaries got kind of ugly with the square roots and stuff. It wasn't that we couldn't do it, but it can be significantly easier to think in terms of polar coordinates. In rectangular coordinates, we use the horizontal and vertical positions of a point from the origin to specify the point xy. In polar coordinates, we specify that same point with a radius r and an angle theta. So we specify it as a radius and an angle. Well, after all, if I told you that you were in 2 dimensions and you were at this point, I don't know, 2, 3, then sure, I could give you the point 2, 3, but I could also think about that point as being a certain radius lying along a circle, the outer perimeter of a circle, and I could give you that point in terms of the length of the distance from the origin as well as the angle, which we can call theta. So to build that, I can make this into a right triangle and say the x component and the y component and r are going to be related in the following way. We could say that x, or rather cosine of theta, cosine of theta is going to equal x over r. And so that means that if we also solve this, we would get x equals r cosine theta. But and so for y, we have the relationship that sine of theta equals y over the radius. Now we know what x is. X is 2, but we don't know what r is, and we don't know what theta is. And y is 3, but again, we don't know what r or theta are. However, we do know the Pythagorean theorem that x squared plus y squared equals r squared. So we have x and y, so we can find 2 squared plus 3 squared equals radius squared, and that will lead us to r equals the square root of 2 squared plus 3 squared, which is the square root of, what is it, 13, I believe. And so in this equation now up here, we can solve for theta because now we know that cosine of theta is equal to 2 over the square root of 13, and sine of theta is equal to 3 over the square root of 13. So we can find theta in either one of these two equations by finding the arc cosine of 2 over the square root of 13. So with those two measurements, all I need to give you is an angle and a radius, and you can then compute the volume of, you can then compute where that point is in location. So whether you specify it by an xy pair or by a radius and an angle, you will still be able to specify that location in two ways. But here's the idea. So if we have this circular region in our two-dimensional space that we want to find volumes between that and our surface, then one of the things that we can do is we can think about this as taking that circular region and breaking it up into a series of individual d thetas. So each one of these little gaps is going to represent a change in theta, right? So theta goes from some angle alpha to some angle beta. And so within each of these strips, so to speak, these are just like our strips that we created in 2 dimensions. Each one of these little gaps right here is going to be a d theta, and another d theta, and another d theta. Right now we're kind of calling them delta theta because they're not yet infinitesimally narrow. And then also what we'll do is we'll break these up from, let's say we just wanted the volume underneath the surface from this circle to this circle. Well, now we want to start our radius at some value a. So this should be radius equals a to radius equals b. And so what we're going to do is we're going to break these up into little drs. So each of these will be a dr and a dr. And so you might imagine that what we're now looking at is each one of these is roughly a rectangle. Not completely, but the smaller you make theta and the smaller you make r, the more this begins to resemble a rectangle. So how do you find the area of each one of these rectangles? Because we know we could sum these up with the integral, but how do you find the volume of each one of these? You can't really just measure or multiply the change in radius times the change in area, by the change in theta, because theta is unitless. Theta is a measure in radians, and that doesn't have any units. But what I do know is that this is the length of an arc. This is an arc length. And arc length, from some trig, we know that arc length, often written as s, is equal to the radius times the angle. So we won't delve into more than that at this point. So what I want is this arc length, which will represent the length of one of the sides of this roughly rectangular shaped region, then I have to multiply the radius times the change in theta, because this thing here is just one of these little segments. So to find the length of that, I have to take the radius and multiply it by that delta theta. So to get my total area of each one of those, I need to say d area is equal to the width by the length of that rectangle, which is delta r times r delta theta, or I could write this as r times delta theta. And so as delta r and delta a become infinitesimally narrow, we use r dr d theta. So that's the change in area. That's the area of each one of these little rectangular shaped guys. Or dA equals r d theta dr. Here, it's not going to matter really at all whether you decide to go dr d theta or d theta dr, because these boundaries will almost always be constant. And another thing we're going to have to do is, if we change our variables of integration to r and theta, we also have to replace x with something in terms of r and theta. So we know that x is equal to r cosine theta because of our right triangle trigonometry over here, and y is equal to r sine theta. So we're going to have to replace x and y with the relationships between r and theta. And sometimes Pythagorean identity will be useful as well to replace x squared plus y squared equals r squared. Now trust me, these are super quick to set up. We're not going to do them by hand, but the polar integral calculator will do this for you. So in this problem, suppose we have the density of people in people per square mile is given by an estimate of f of xy equals 600 minus x squared minus y squared, where x and y represent the east-west and north-south distances from the city's downtown. We want to know how many people live within 10 square miles of downtown. All right, well, what that means is that we want to find, and I'll go ahead and sketch this. We have a downtown region, and that downtown is located right in the center. And then we have this should not be 10 square miles, it should be 10 miles of downtown. Okay, so this radius here is going to be 10 miles. And what we have is, if we know the density function is f of xy equals 600 minus x squared minus y squared. That's in people per square mile. Now I want to know how many people. I don't want to know how many people live per square mile. I want to know how many people live within a certain overall region. So I've got to multiply that by square miles. Now, the number of people per square mile is obviously not constant. The farther you get away from the origin, the more we're subtracting off 600. So the population gets less dense as you move further and further away from that center. Now, here we go. If we set this integral up as a double integral in polar coordinates, in rectangular coordinates, we'd have to do something like x goes from -2 to 2, and then y goes from the bottom of the circle to the top of the circle. It's not that it can't be done, but it does incorporate some square roots in there. But let's go ahead and say we did r dr d theta. That means my inner integral is going to have to be the boundaries for r. Okay, so r goes from 0 to 10. And it's really that simple. Your radius is from the origin, from r equals 0 to r equals 10. And then we now want to specify the theta. Well, the theta is the overall angle. So imagine that to be from the x-axis. We want the angle to go all the way around from 0 to 2 pi. Because we want to know, if we wanted to know just like, say, the density of people within the first quadrant, we could have theta go from 0 to pi halves. If we wanted just a half circle, a semicircle, we could go from 0 to pi. We could even just find the area of this region by going from pi to 3 pi halves. And that's the beauty. We have such control over our angle, but in this case, our angle is from 0 to 2 pi because it's the full circle. What I have inside of here is the density function, 600 minus x squared minus y squared. And if we again analyze the units of this, this is in people per square mile, multiplied by radius. Well, radius is measured in miles. dr, change in radius, is also measured in miles. d theta is unitless because it's a change in angle. So you get miles times miles is miles squared, divided by miles squared. Those cancel out and we get total people. Before we complete this integral, however, the thing that we have to remember is that we can't have x and y in here. We have to get everything in terms of r and theta. So I could just replace x with r cosine theta and replace y with r sine theta, and we'd be good. So we could just write this as the integral from 0 to 2 pi, integral from 0 to 10 of the function 600 minus, okay, so replace x with r cosine theta squared minus quantity r sine theta squared. And that's going to be times r times dr d theta. Another thing you could do here is if in this parentheses you observe that this is really 600 minus quantity x squared plus y squared, this by Pythagorean identity is the square of the radius, so I could make this integral a little bit easier. Again, I'm going to dump it into an integral calculator, so it doesn't matter, but at least the input will be a lot shorter if I just say this is 600 minus r squared times r dr d theta. And you could also see that here if you do r squared cosine squared theta and factor out an r squared from both of these terms, r squared cosine squared theta, or minus r squared, factor that out rather, plus sine squared theta. Cosine squared theta plus sine squared theta is Pythagorean identity, which is 1, and then you get 600 minus r squared that way as well. So to dump this into the integral calculator is pretty straightforward. We would, if I can find the right page, here we go. So now here it's using f of r comma q, so q is in radians instead of using theta. So let's go ahead and type in our density function, which is 600 minus parenthesis 600 minus r squared. Now you do need to put this in parentheses. I'll show you what happens if you don't, because the integral of variable of integration already has r dr d theta. R goes from 0 to 10. Theta goes from 0 to 2 pi. That's already good. Now when you press go, you get 600 minus r squared quantity times r dr d theta. So there's about 172,788 people living within 10 miles of downtown. If I omitted the parenthesis here, this is kind of just a glitch in this technology, that what's going to happen is something really odd now. We're going to get a different answer. Now the r is multiplying the r squared, but it's not multiplying the entire 600 minus r squared like we wanted, so we get a different answer. So we just want to make sure that whatever function we put into this double integral calculator, we wrap it in parentheses. And so when we submit that, we get an answer of 172,788 people. Now we could also answer more interesting questions like how many people live between 5 and 10 miles north of the capital city. So the picture we're going to draw is going to be much more complex in the sense that rectangular coordinates would be sort of tricky to have to set up. So we just want to look at north of the capital city. So that's just going to be above the x-axis. And we want to know the number of people living between 5 and 10 miles. So basically what we want is we want the area between these two circles. And this could actually be quite a difficult integral to try to set up if you're not using polar coordinates, because of the fact that you'd have to actually set up a couple of different integrals, especially since your boundaries change as you move across the function. But with the double integral, all we need to do here is have our r dr d theta, our density function, which we already now know is 600 minus r squared, and r simply now goes from 5 to 10, and theta now goes from, not from 0 to 2 pi, but from 0 to pi. And that's it. We are good to go. We are ready to calculate this. We should get a smaller answer than before because of the fact that we're only looking at the number of people that live on the outskirts of town, really. and the number of people that we get within that region is 63,323. 63,323. Whoops. 323 people. And that's it. We're done. That was a quick one to set up. Now, just as a form of practice, let's say we wanted to take something that is in this really nasty form and we wanted to write it in polar coordinates. So the first thing we should do is try to visualize what it is that we want to find the volume of. So here, x goes from 0 to the square root of 2. So from 0 to the square root of 2. And this function goes from x equals y to x equals the square root of 4 minus y squared. Now, x equals the square root of 4 minus y squared. We could square both sides and add y squared and see that this is a circle of radius 2. And so we have a circle of radius 2, which is going to look, something like this. I'll draw it a little bit taller. There we go. So circle of radius 2 like this. And now we are also bounded with the line y equals x. So this is the line y equals x right here. And we want to find, in this case, because we're going from the line to the circle, to the outside of the circle, we want to find this region here. Well, how do we do that? So first of all, since this is the line y equals x, this splits the first quadrant into 45-degree segments. So these are both 45 degrees, even though I haven't drawn it very well. We can see that these two functions actually intersect each other at the point, this is the point square root 2. And the way we would find that is we would say, well, when x is equal to the square root of 2, we subtract it over from the right-hand side and then take the square root, we would get y equals the square root of 2 as well. And that also satisfies the condition that x equals y, so it's a point on both of those segments. So really what I want to find is I want to find the integral in polar coordinate form. This radius here, remember that radius is equal to 2. And so I'm going to set up my r dr d theta. My radius is going to go from 0 to 2. My theta is going to go not from 0 to 45 degrees. 45 degrees would be pi fourths, but we want to go from pi fourths to pi halves. That's just going to be this region here. And of the function x times y, that's the integrand. So that's the height of the surface of the function floating above this. And there we go. We are done. We have this now set up. Oh, but we do have one problem though. We have to convert x and y into r cosine theta and y into r sine theta. And now we can go ahead and plug this into our calculator. So that's it for this video. We now have triple integrals and polar coordinate integrals under our belts.